In this video, I want to just show you another example of using the method of undetermined coefficients to solve a fourth order non-homogeneous differential equation. So here's my equation. Fourth derivative minus the third derivative minus the second derivative plus the first derivative is equal to t squared plus 4t plus, not 4t, just 4 plus t sine t. And let's find the general solution for this equation. Okay. Now, everything about this process is, well, let me word it this way. Nothing about this process is particularly difficult. It's just that there's a lot of stuff, right? You've got to find the homogeneous part of the solution, and then you've got to find the particular part of the solution. In this case, the particular part of the solution we're going to find in two parts, because I see a polynomial here, and then I see a polynomial times a trig function, so I'll split those up into two pieces to find each one individually. But there's just a lot of space, a lot of paper that needs to be used to do these things, but they're not particularly hard. So here we go. First of all, I got to solve the general solution for the homogeneous equation, so get rid of all that stuff, put a 0 right there. Then I'm expecting a solution of the form y equals e to the rt. And so when I plug that in, I end up with this quadratic equation that we've been doing, the characteristic equation here. In this case, r to the fourth minus r cubed minus r squared plus r would have to equal 0. I notice that there's a factor of r in all of those, so pull it out, leaving this cubic left. Now, actually, I think I factored this cubic in a previous video. I want to do it again in a different way, just to illustrate a different factoring method. This factoring method is called factoring by grouping, which usually doesn't work, but once in a while, nice things happen. So here's a cubic, and what I notice here is that if I group them in the first two and the last two. So for the first two, I'm going to factor out an r squared, so that would be r squared times r minus 1. And then for the last two here, I'm going to factor out a minus 1, leaving an r minus 1. Now, usually what happens is what's left in this parentheses and what's left in that parentheses are different, and this doesn't get you anywhere. However, when they do turn out to be the same, in this case r minus 1, then I can factor the r minus 1 out of that. So from the first term, there's an r squared left, and from the second term over here, there's a minus 1 left. And the r minus 1 got factored out. Okay. Again, this is not the usual outcome. This is a special case when factoring by grouping works. But that gets me down to a quadratic, and the r squared minus 1 I know factors into an r plus 1 and an r minus 1. So there we go. This gives me 3 solutions, 4 actually I guess, but one of them twice. R equals 0, r equals minus 1, and both of those two terms equaling 0. Sorry, those aren't terms. Both of those two factors equaling 0 give me r equals 1. So that gives me a general solution of the 0 gives me a constant, right? Because e to the 0t would be 1, so 1 times that constant. And then the minus 1 gives me e to the minus t, and the 1 gives me an e to the t and a t e to the t. So there's the general solution for the homogeneous equation. Now, there's 2 reasons why I do that. One is I need it for the general solution for the equation I'm actually trying to solve, the one out here at the top. But also, when I'm making guesses for the particular solution, I need to be comparing them back to the homogeneous solutions to know how I might need to adjust my guesses. Okay, so here we go. To solve for the particular solution, I'm going to do it in 2 parts. I'm going to do the left-hand side equals the polynomial here, and then I'm going to come back and do the left-hand side equals this product of a polynomial and a trig function. So to do the first part, I'm seeing a quadratic polynomial, so I'm going to guess a quadratic polynomial. The general quadratic would be a t squared plus bt plus c. However, this I know will not work because the plus c is part of the homogeneous solution. So what I need to do is I need to multiply by a power of t until nothing in here is. That's, in this case, just multiplying by a t will work. So that gets me to an at cubed plus bt squared plus ct, and here we go. Take the first derivative, take the second derivative, take the third derivative, and take the fourth derivative, and then plug that all back into the equation right here, and see what has to be true about A, B, C, A, B, and C. Okay, so here we go. There's the fourth derivative minus the third derivative minus the second plus the function, no, plus the first derivative equals that polynomial. So when I gather some like terms, so I look, there's only a t squared here, so it's 3a times t squared. There's a minus 6at there, and there's a plus 2bt there. So 2b minus 6a times t. Is that 2b, or should it be something else? It's 2b. And then the constant terms is a minus 6a. There's a, there's the not 2b, and there's a plus c. So the constant terms are there. If the polynomial on the left is equal to the polynomial on the right, then all of the corresponding coefficients have to be the same. So the 3a has to equal 1, the 2b minus 6a has got to equal 0, and the c minus, the c minus 2b minus 6a has got to equal 4. So this first one gives me that a equals 1/3. The second one that says, let's see, solving for b, it should be 3 times a, but a was already figured out to be 1/3, so b is 3. And no, b is 3 times 1/3, which is 1. And then plugging in for b and a, I can figure out what c is here. And c turns out it is 8. So the particular solution that satisfies not the original differential equation, but this partial one, right, that just with the t squared plus 4, the solution would be 1/3 t cubed plus t plus 8t plus t, 1/3 t cubed plus t squared plus 8t. Now we're going to find y2, which will be a solution for this part, so the same left-hand side, but just this. Now, when I first sat down to do this, I actually did it wrong. I made a wrong guess. I said, oh, I know how to do this. I need a general linear times a sum of sines and cosines. And so I had 4 coefficients. I had an at plus b for my general linear factor, and then I had c cosine plus d sine t. And I tried to solve it, and I kept getting contradictions. It's like, why doesn't this work? Well, it didn't work because the form of my guess was wrong. My form of my guess was not yielding a solution. If you take a look in the text, this is back in this, when we were doing it for second order differential equations, they gave a table of if your function looks like this, here's what you should guess, and so on. So when you had a polynomial times sine or cosine, what you needed to do was the general polynomial of the same type, so this is linear, this has to be linear, then times sine. If this was a sine of 2t, this would have been a sine of 2t, but anyway, times sine, and then another linear times cosine t. Now, what I was trying to do, by the way I was setting it up, was I was trying to make those two be the same polynomial, and that is not the way it works. It didn't work the way I tried, and so it's like, what am I doing wrong? So this is what I have to do instead. If the t sine t happened to be part of the solution for the homogeneous equation, then you would have to multiply this by t, or t squared, or whatever, until you got to something that was not part of the homogeneous equation, right? Even if there was a sine of, even if sine of t without the t was part of the homogeneous solution, you would have to multiply here by t, because the b sine t would be not contributing to the non-homogeneous part, it would be contributing to the homogeneous part. But in this case, t sine t is not part of the general solution, nor is sine t, so I can just make this guess. I distributed it through here just because I find it easier to do all the derivatives written out like this and then keep track of things. So what I notice is that I have a t sine t, a sine t, a t cos t, and a cos t, and that every derivative, as we'll see, has all those pieces in it as well. So, for instance, the first derivative, there's a product rule here and there's a product rule there. So there's the product rule for the first one, and there's the product rule for the second one. And then I gather some like terms. So I've got something times t sine t, I've got something times sine, I've got something times t cos t, and something times cosine t. So I arranged them in the same order as those, but we have different coefficients out in front now. And then you take the derivative again. And actually, if I had thought about it when I was doing it, that a pattern is set up here, because each time I have the same pieces, and this one is telling me how the coefficients are going to move around. But anyway, do a product rule, derivatives of sine and cosine, and gather your like terms again. And there's a second derivative, and the third derivative, and the fourth derivative. I mean, this is not hard. It's just a lot. You just have to keep taking derivatives. Now that you've got all those derivatives, you can plug them in. So the fourth derivative minus the third derivative minus the second derivative plus the first derivative, and set that equal to t sine t. Now I put dot 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 here. This is you can do the work. What I then look at is once all those things are added up, what are the coefficients in front of t sine t? What are the coefficients in front of sine, t cos t, and cosine t? Right? And what I know is that I need to have a 1 in front of a t sine t and a 0 in front of all the others. So for instance, the t sine t, I see there's an a here, and from here there's a c, but I'm subtracting this third derivative. So I have a minus c, and then I'm subtracting this one, which is, so then it becomes a plus a, and then I'm adding this one, which is minus c. So this first equation, a minus c plus a minus c equals 1, that is looking at the coefficients in front that you're getting in front of t sine t and saying, hey, they have to equal 1. The second equation here is looking at what's in front of sine. So there's a b plus 4c, that's right there. And then on the next one up, there's a minus 3a plus d, and I'm subtracting that one. And then I'm subtracting this one, and then I'm adding the one that's just off the screen here, right there, that a minus t. So there's that equation. And likewise for the t cos t and for just the cosine. And each of those three, this one, and this one, the coefficient has to be 0 because it doesn't appear up here. So what I have here is 4 equations in 4 variables, and I can solve them. Although it turns out that the first and the third equation here are really nice, because this is 2a minus 2c equals 1, and this is 2a plus 2c equals 0, and then it's really easy to just add those equations together and find that a has to equal 1/4 and c has to equal minus 1/4. Once you know a and c, then you can plug them in to these other two, and then you have just 2 equations with b and d, and you can solve those as well. And it turns out b is 3/4 and d is 1/2, which makes y2 the this right here, 1/4 t sine t plus 3/4 sine t minus 1/4 t cos t plus 1/2 cos t. So that is a particular solution that will solve this differential equation right here. Putting those two, y1 and y2 together now, and the general solution to the homogeneous equation, we get that the general solution to the original non-homogeneous equation is all of this stuff from the homogeneous part plus this part plus, I didn't put the other one in here. There we go, quick edit. So the homogeneous part, the part that this is y2, those 4 terms for y2, and then you've got the 3 terms from y1. And this right here is the general solution of that original non-homogeneous 4th order differential equation. So there you go. Again, not difficult, just a lot. And many, many places to make small errors, which of course then throws everything off. Anyway, of course we could make this even more fun by then giving initial conditions and saying find C1, C2, C3, and C4. Yeah, but I'm not going to do that.